One of the basic principles of geometry has to do with parallel lines and opposite angles, and we extend these basic principles further. For example, if we start with two parallel lines, we always mark two parallel lines with two like arrows. So for example, single arrow now means that these two lines are parallel. They are always a fixed distance and they will never cross no matter how far you extend them in either direction. If we take another third line that goes across here at a random or oblique angle, this is now said to be a transversal. Trans means across, and ver, root, means going towards something. So the line goes across. It is not parallel, so it is not marked with an arrow, at least not a single arrow. If we take a look, we can satisfy ourselves that the opposite angles in either case, if I just bring it back now to two lines, which are not parallel, we could satisfy ourselves any number of different ways that this angle here, which I'll call x, is equal to this angle here. For example, we could, if you did this on a piece of paper, and I'm not going to try to fold my whiteboard because it's too stiff. If we were to fold a piece of paper so that it bisected each of these other angles, we could fold it on the dotted line here, and you would find that these two angles, x and x, are exactly the same size. You could also do it the other way and satisfy yourselves that the other angles, let us call them y, were the same size if we were, for example, to fold the piece of paper the other way, say along this dotted line here, and you would find that angle y and y coincide exactly. Therefore, they are the same size. So going back to our original example, if we take our original line and our parallel line and our transversal, we can extend the idea so that it becomes obvious that this angle here, x, is the same as this angle, and it's also the same as this angle and this angle here, because our parallel lines, starting with the bottom one, if we just slide it up, the angles with regards to the transversal have not changed. So x down here in the bottom left is the same as this x right there, and so on. We can go a bit further. If we put a second transversal in here like this, this is now parallel to the first transversal, so we put another marking, but we do not use a single arrow because it would imply that this line is parallel to this line. Single arrow, single arrow. Therefore, we could use a double arrow and a double arrow. But that's not what I'm going to show you at this point here. Let's go to triangles. So if we get rid of these extra lines here, and I put another transversal here which corresponds to that point of crossing there, we have now created a triangle which I will outline for you in blue. So, blue, blue, blue. Following our opposite angle theory, we now know, of course, that this angle here, which I'll call y, is the same as this angle here, because this angle and this angle are effectively opposite angles. Because this angle here is the same as this angle here. Yes, I know it's getting a bit messy. Just follow through or replay the video. So this angle here is, of course, the same as this angle down here. Now, we come to another interesting extension conclusion if we take a look at these angles and see how they fit together. Because, I'm running out of colors, but what we have is angle y, angle x, and the third angle of the triangle, which I'm going to put across here with the double line, form a straight angle. If I were to draw that a little bit further down here to get rid of all this overlap, we have our original straight line, which is here. We have our two transversals that meet at the same point. We have angle x, we have angle y, and of course we have that last double angle, which I suppose I could call z, but it doesn't really matter. These add up to our original straight line, which by definition is 180 degrees. However, we also notice that x plus y plus z form our triangle. If we do this with any triangle, we will find that a triangle always adds up to a straight angle or 180 degrees. Thus we know and have proven that every angle has its opposite angle when two lines cross, and every triangle, if you add up all three of the angles, can be proven to equal 180 degrees exactly. If this math hurts your head, like one of my friends just said recently, now my brain hurts, you could either wear a helmet, but I suggest you remember that no matter how much your teachers at school love you, we love you more.